right before the start of the lecture. This is a great way to not minimize attendance, but to decimate attendance. That's good. I'm hence particularly happy to see all of you here, right? So either you did not hand in an assignment, that's okay, it doesn't make me happy, or you did it well on time, but I'm going to go with the second option, and maybe there's third or fourth, but I don't know. Good. Before we get properly started, Zoom, can you hear me too? Let's see if 1 out of 14 people respond. Yes, very good, very good. Okay, and almost time to get fully started. Let's first take a sip. Okay, good. Yeah. Let's see. Before I get really started with this lecture, there's a few things I need to discuss with you. To begin with, we still have a few slides left from last week's lecture. So before the fourth lecture really starts, we have to go back in time, but okay, such is life. Now, there's a few other things that I wanted to mention, given that we're now a number of weeks into the course, and well, things are, we're getting in full motion. Now I've done the first assignment sheet, you've hopefully managed to upload it, and so on and so forth, right? That is both scary for you as well as for us, because we're changing. Yes, it is, Atfried, it is scary, and I dare to admit that. This course was never this big, and we've changed many things. And yeah, changing too many things makes it very scary on our end. So I hope that we change the right things the right way. Let's see. So I hope that the submission instructions, that they were clear, that you didn't have any problems submitting your assignments. And we also hope that the assignments themselves were sufficiently doable, challenging, yet doable, right? So we're going to see, our tutors are going to grade the assignments over the next few weeks. And the idea, the hope that we have is that roughly 2 weeks we have the grading out. But yeah, the first assignment, there is a massive number of students, so we need to see if we can squish this in, right? So I ask for your understanding if it takes a few days longer, right? We really work our asses off to get it done as soon as possible, but yeah, we have only limited person power. Good. Otherwise, there's a few other things I wanted to mention. First of all, it seems to be going very well, in the sense that I see good activity on the forum, of the right kind, right? Not the, oh my God, what is this? That's good, that's good. I get relatively few emails, which is also good, because if you send me an email, chances are 99% it's going to somehow disappear in a big avalanche that I get on every day, right? It's not that I don't want you to email me, but if you want an answer, it's better to play it through the TA's channel, and they have more time on their hands. So far, we also got a few comments through the comment system on CMS. And a number of those were praise. They liked the lectures. It's nice to hear. That's nice to hear. I like that. I'm not soliciting for more praise per se, but if you have it, right, I'll take it. I'll take it. There were also a few suggestions what we could improve. For example, already in the first week, there was somebody who suggested that we should use a different forum. And problem is a little bit, we kind of can't, at least not on short notice. I totally agree. The discourse forum that the other CMS uses, which is a fork of the original granddaddy CMS, that is the CISPA one. Yeah, I like that forum better too. But we are kind of right now in the current setup, in the install we have, we're dug to BB forum, PHP BB. I'm with you. Perhaps next year we have discourse or something even better. The fix that we did this year is to make sure that the current forum does support LaTeX. Because previously it didn't, and yeah, if you want to discuss mathy stuff, then indeed, I mean, that's a bit stupid if it doesn't. What I wanted to say is that I very much like these suggestions, and B, wherever we can, we take them into account, right? What is good, what can be better, and so on and so forth. So keep it coming. For example, one of the other comments that we got was on the tutorials, that right now, some of you might find them a bit lectury. We hear you, we hear you. You see how we adapt this. One of the problems we have there, not to be defensive, but we have only very few TAs. We have many students, and the ideal setup would be 10, 15 students, 1 TA, really lots of interaction. That would be ideal. I would love to teach that course. But we have 370 students signed up. just do the math of how many TAs we would need, or how little time such a TA, who is a PhD student, who is literally volunteering, right? They're not being paid to do this. How much they would. So what we currently have is a bit of the best that we can currently do. We're trying to think of how we can improve. If you have suggestions, let me know. Okay. The last thing in that line I want to say, and this is really a compliment. You are not necessarily those here in the room, perhaps, I don't know, no way of telling. Perhaps you're on Zoom, perhaps. Okay, just one question, I will answer the second. Perhaps the ones listening on YouTube, but you seem to be the nicest batch of students that I've been teaching in the last, I don't know, 5 years, 6 years that I've been teaching EML. But the emails and suggestions we've gotten, they were all polite. And I like that. I really like that. So thank you. Thank you for being polite. This sounds stupid, but you don't want to know what you sometimes get as emails. Like, okay, this is really, excuse my French, but what the fuck is this shit? That really, I haven't gotten this, and I don't expect this. From the baseline we've now gotten, I'm really, really happy. So I hope this also goes the other way around. Good. So the question by Lewis is whether we can make an estimate on whether the changes we've made contribute to your success. 100%. 100%. Every change has been made in your interest. It's not in our interest, okay, how can we minimize our effort? It's really how can we deliver the best lectures, the best tutorials, and so on with the resources we have. If somebody would give me, I don't know, 100 super talented PhD students who are willing to, yeah, sure, we can make it better. I don't have 100 PhD students, and I also don't want to supervise them because that becomes a nightmare by itself. For example, one of the changes that we made is that we're going to be releasing the sample solution for the assignment sheets. We're going to be doing this probably tomorrow. Originally, the plan was to do this today, but again, I made a small change in your favor, just to make sure that if anybody fails to submit their assignment right when they should, because of technical difficulties, and yeah, the moment that then immediately the sample solution is out, then I have to say, I'm sorry, maybe you copied. Even though I also know that nobody can copy in 1 minute, unless it's verbatim, right? I mean, then I can tell, So right now, because everybody needs to get used to the submission system, it will be the release tomorrow. The next few I plan to release on the day itself. I think that having the sample solution, which we didn't used to do in the past, and most courses, most lecturers I speak to also don't do this, I think this is to your benefit because it helps you to study. Whether this in the end is indeed the fact, I don't know, right? That's the experiment part, but the change is made in your favor, I think. Good. Okay, so with that said, I would like to get started, but not with lecture 4. I want to get started with lecture 3. Good. So, very short recap. What have we been discussing in the last 2 weeks? Given essentially a scatter plot, how to draw the best line. That's in a nutshell what we've been doing, right? And well, we've learned how to do this when the scatter plot is 2D, when it's 3D, or umpteen D, right? We also learned what is now best, and so on and so forth. All good. Now you might remember in the first lecture that for classification, we had this super simple method, which was essentially, well, what is the value of your k nearest neighbors? Give the majority vote, and that already worked, right? Well, can't we do the same thing for regression? Yes, of course, no problem. How well does this work? I mean, why didn't I teach this earlier? We'll see. So KNN, k nearest neighbors based regression, is very similar as the classification variant, except that right now we don't need to make a decision, so there's no majority vote. What we do, we simply look for a query point, typically called x0. We look at the k nearest neighbors using some distance measure, often Euclidean, but whatever you prefer as your distance measure, I mean, do try. We take the values of those k nearest neighbors, take the average of them, that's what we put out. Easy peasy. Now, just like in the first lecture, bias variance. Just like in the first lecture, high k, high bias, low k, low bias, but high variance. So we have a trade-off. Small values of k, you get a complex model. We have an example here on the right-hand side, where we said k is 1, literally, what is the one nearest neighbor, and you get this super staircasey pattern, right? That's in your decision landscape. Okay, so now if we increase k, we get a slightly smoother landscape. It is still staircasey, but it starts to behave slightly differently because it might be that in the one dimension, well, neighbors of one point is a bit more to the left and the other one is a bit more to the front. So it doesn't follow the staircase pattern step by step. Now, the higher the value we push it, the more it starts to just become a plane, and that's that. So it becomes actually not a fixed plane. It can't really go into this kind. So high bias model becomes too smooth, not good. How do we find the optimal value of k? Well, we still have to postpone that. Now, which model should we use? KNN, super easy, and well, I give you my word, we will learn how to choose k. Wait a second, does Zoom see? No, Zoom doesn't see the slides. That is unfortunate. You didn't miss so much, Zoom. I'm sorry. Just to make sure that Zoom saw the slides. This was the slide with, well, the not staircase. This is the slide with the staircase. Anyway, the slides are online, so you can download them. That's good. Now let's see. Where does linear regression stand in the comparison? Where does KNN stand? And when should we use the one over the other? Here on the right-hand side, I have a number of examples, all where the true function is strongly nonlinear in the first variable, right? So it's polynomial in x1. And the rest, just nonsense, just random variables, nothing to do with the value we want to predict. What we see is that if we now, let me aim it like this. Now we only have this first variable. When we look at the errors, well, the dashed line, that is the fit that we get from linear regression. Not bad, but we also see that KNN has a lower mean squared error. So it's already pretty good, right? So it's nonlinear, KNN beats linear. Can we draw that conclusion just like that? Yes, but no. Yes, but no. Because if we now add more irrelevant variables, here we add one. And it's difficult to see, right? The screen here is big, but you can, well, whoops. No, it's even more difficult if I look over my shoulder and try to aim it. This line is already slightly, ever so slightly higher than for PS1. We already see a little bit of an effect that, hey, adding nonsense variables, nuisance variables, noise, KNN starts to become confused. For 3, all of a sudden, depending on which k we choose, we either get a worse model, this is with a low k, or if we choose k high enough, okay, we can just barely beat linear regression. On the lower row, I'm not going to point them all out, but there we have respectively 3 random variables, 9 or 19. And as you can see, especially for the 19 one, well, no, you should not use KNN if there's 19 random variables. Random in the sense that they have nothing to do with your predictor. I could say, okay, well then just use KNN for low dimensional cases, but yeah, that's also not entirely true. Here, this is the case where the relationship is strongly nonlinear. So we already put the linear regression at the disadvantage, right? Bless you, by the way. So if it would truly be linear, then KNN's ass would be completely beaten. Completely beaten. What we see here is a phenomenon called the curse of dimensionality, or one of the guises of the curse of dimensionality. Which is to say, more data, more predictors. Sounds good, right? More information, yay? Not quite, not quite. Just like what we saw in multiple linear regression, if I give you more and more predictors, you need to estimate more and more coefficients, which means you need more and more data. And as I mentioned, you need an exponential amount of data and the number of parameters you need to estimate. Otherwise, the model is underdetermined and you never know which one is now really truly best. That's also what you see here. KNN can perfectly well handle 20 relevant variables with the right distance measure. But the moment that there's 19 irrelevant ones and only one relevant one, and you measure over the entire row how similar are these, basically the signal, which is just the value of the first variable, gets drowned out by the similarities of the 19 other ones. KNN has no way by itself to choose which variables to listen to. It's completely non-parametric, does not allow for inference, right? There's no model being built. With linear regression, multiple linear regression, especially with the right basis functions, we do have a chance to find those sets of variables that are particularly informative. Strong coefficients, significant, and so on and so forth. Good. See, is there anything else interesting on the slide? Not so sure. Yeah. No. Basically, KNN assumes that the world is locally constant, whereas linear regression assumes that one model fits the entire world. KNN says, okay, no, the world is a messy place. There's many local models, but it doesn't really have power to model these local spots. Right? This is the staircase type of pattern. Now, what I don't want to go into today, but some of you may already have the thought, what if we would marry KNN and linear regression? What if we would look at the k nearest neighbors, and rather than just reporting the average, why don't we do some sort of regression over this? I can only say yes. Yes. Because I said I would not say anything further about this. One further example of how this now behaves, when it does well, when it doesn't do well. Here we have linear data. We compare linear regression to KNN. On the left, we have an example where what is the fit of linear regression, and the blue line is the fit, very close to the population line, right? So pretty good. If you now look at the fit of the yellow and the red model, 1 nearest neighbor versus 9 nearest neighbor, is a mess, right? And especially the red one goes all over the place. The 9 nearest neighbor becomes a bit more smooth, in this case good, but still it's very hopsy. And on the right-hand side, we then see that KNN fit is indeed worse than the linear fit. Let's go to slightly more nonlinear data, mildly non-linear. Let's say a polynomial with a low degree. Guess this is a 3rd degree at the top of my head. Linear regression is starting to have slightly more trouble here because it can only fit a straight line. So, and we see that for the right value of k, we can beat it. This is basically an excerpt of the plots I showed you earlier on the right-hand side. Now, let's now go to properly nonlinear data and really bend it down. Whether it's still, that could still be cubic. Maybe it's something else. I don't really care. But clearly, this data can't really be fit by just a straight line. And now you see that essentially, whatever value of k you choose, k is 1 is all the way on the right, k is whatever the number of data points is on all the way on the left in this plot, you beat linear regression with ease. So KNN is a really good fallback method if you have a nonlinear process and you don't have too many variables that are irrelevant. That's something that you can wish for, you can partially test for, but you need to be very careful with. This is basically what I wanted to quickly recap on KNN. Right? So now I can say, well, thank you very much for your attention. See you again next week. And I'm quickly going to change the slides now. And now I realize I should have brought 2 jackets, and I could quickly have switched. And at least in the recording, it would have merged it. Come on. You're doing PowerPoint. This time I'm not going to forget Zoom. Okay, good. Well, welcome once again. Let's talk about classification now, right? So what is the big difference? We right now stop caring about continuous valued outputs. Somebody, I believe it was you, who last week already asked, okay, what if we don't have a continuous, oh, that's welcome. That's happy that you're here. So we want to predict categorical outputs. A lot of the examples I'm going to give today, well, there's 2. It's called binary classification. But in general, classification can be with umpteen categories. Right? The main idea is that we cannot really order these categories, right? Just like is it yes or no or yes. I mean, red, blue, green. Yeah, these are 3 different colors, right? Because of course there's also sort of an intermediate case between continuous valued and categorical. If you have ordinal data, right, in low, medium, high, and then you're a little bit in the middle between these 2, use regression rather than classification, but that doesn't always hold. Good. One of the examples that we're going to be using today is similar as last week. Is somebody, well, it's a financial, it's credit data. In this particular case, we're Play Bank, and we're interested in whether if we give somebody a loan, are they going to pay it back? Yes or no? And we need to make this decision on, well, what income they have, how much money did they already loan, right? From me, from otherwise, whatever. What is their employment status, right? I mean, and so on and so forth. Huh? So we need to make a yes/no decision, loan or not loan. Here we have the example where we have annual income and the credit balance. So, and in the end, we also have student status. Not shown in this plot, of course. So, what we have is that, actually, besides that, I've been talking all day long, so I'm super thirsty. On the right-hand side, we want to predict, is somebody going to default? Default is the word, I mean, the technical term for is somebody not going to pay back their loan. So because somehow the default option is that people don't pay back. It's very pessimistic. But hey, what is it? And what we have is that here. So the people who do not default, so who are going to pay back, they typically tend to have a very low credit card balance. So how much they already borrowed. People who are more likely to not pay back, not really shocking. Now, there's one group, students, not students, for which this kind of breaks down. So here we have two groups where there's a bit of a difference, but not so much. So, if you do not take this into account, studentship, you're going to not give out loans that actually would be paid back, because as students do graduate, they are going to make money in the future, right? So you kind of need to take this into account. Okay, it's a bit related to what we saw already last week, right? You need to take factors into account, because otherwise it's just an offset, and actually there is essentially the regression model behind it is two lines that are not parallel. Some other examples, for example, you want to classify whether, based on symptoms, whether a patient has a particular disease, yes or no, or which variant of a certain cancer do they have. Because variant A we treat with this drug A, variant B with drug B, and variant C, well, okay, better wait it out until we have drug C, right? So we need to be able to classify this. Because if you do it the wrong way around, you could have drug A to patient of class B, then they might suffer a horrible, even more horrible death. Intrusion detection is or actually, this is more transaction verification, but let's say a bank transaction, is this fraudulent or not? Or intrusion detection, there is some request within your network, is this genuine, or is this something we should block? It's basically what your firewall is doing all day long. You can also flip it a bit around, more towards inference, so classification-driven inference. Suppose we are now interested in finding those mutations of people that are particularly likely to develop a certain disease, right? So now we're not so much interested in, are they going, but what are the mutations? We need inference there. It's a classification-driven inference task. Okay, I hope that besides, what is your name? Edouard. Okay, so besides Edouard, that everybody is now also sufficiently convinced that this is a useful task. Okay, well then, first things first. Last weeks I've been telling you linear regression, right? And we're just going to crank it up all the way to the max, and then in the end, right? Well, it's still linear in a way, but my God, what can it do? So the right question to ask is, how about linear regression? Here we are. Linear regression can actually work for binary classification. So what we need to do, we need to simply code our target variable 0 and 1. And then what we do regression, tries to find the line where it's close enough to the ones, and then basically whatever the line then says, right, for a given input, that's going to be our output. Great, works. So essentially we're trying to find here a line. that separates the classes, right? So if a point is now above, then we're going to say it's orange. If it's below, then it's going to be green. Same thing over here. This works. However, not really the best thing to do. I'll show you in the next slide, a bit more visually, a bit more intuitively, what goes wrong. But one major problem that you can immediately see, what if we don't do binary classification, but what if I have 3 classes or 4 or 5? Well, in theory, we can still make it work, right? We have an example. We just have now, we have green, red, and blue, and I just call them 0, 1, and 2. I have a continuous output variable. I can do linear regression. No problemo. However, I could have also coded them red, blue, and green, and so on and so forth. I could have given them different numbers, not 0, 1, and 2, but 0, 3, and 9, all of which would have resulted in a different model. And that's where things then become very tricky, because what is now the best coding for binary, 0, 1, or 1, 0, or I mean, you can scale them, right? You can have 0 and 10 for all I care, but it's going to be the same. Here it's not, and there's essentially no way of telling which one is best. So for binary, okay. For multiple, nope. There's one exception. If we know that these labels, red, blue, green, if they are metric, so if there is a real distance between them, we know these numbers, so we can guesstimate them, and it's fine. But then we're exactly in this gray zone that I pointed out earlier. Then we're not really in a pure classification task. We're more in an ordinal regression / classification task, right? Which of the 3 is it? What is the order? If you know that, and you know these values, go ahead. Otherwise, be careful. So here on the right-hand side is another thing that goes wrong if we use plain linear regression. Essentially, we have here then balance data, and what is the probability of somebody then defaulting, yes or no, right? And as you can see, well, people with a very high credit card balance, they're over here, low balance over here. So this is then essentially the line that we would fit. Now, you can see it doesn't really separate the two. It gets dragged down, so it really looks a bit bad. But if we now interpret this, we would like to interpret this also in a sort of probabilistic manner. What is the probability of somebody defaulting? What is the probability of somebody having disease A versus disease B? Would be nice to have. Linear regression, we don't get this, because we just get a line, and this line doesn't speak probability. So what we get is a line here that happily goes below 0, right? And yeah, I'm now, is it 15, 16 years in the business, but I still don't know what the negative probability is. It's a bit tricky is. So we get values out of 0, 0, 1. We can't interpret this as a probability. So yeah, Can we fix this? Does anybody have an idea? What could we do? No? Exactly. We could try to project it to another space, but linearly separable, yes, yeah, that would be one suggestion. So basically right now, we can't really draw a line between the two. So if I would somehow magically grab these points and I throw them up way more to the right, that I really have the good points here, the bad points there, then it's very easy to draw a line. That's what you mean, right, Jabat? Yeah, that's how you can interpret. This is essentially what a kernel method does. We're going to be discussing kernel methods, I think, in lecture 9 or 10, something like this. So you're a little bit ahead of the game, One other thing that we could do is, in a way, much simpler. We can take the values that we get out of this line and we rescale them between 0 and 1. And then all of a sudden the problem is gone, right? Now, one way what we could do is, and you don't want to do this, we could simply raise the line a little bit, add a bit to the intercept, and then scale it to 1, and say, okay, well, this is the interval over which we look, right? 0 to 1, everything is fine and dandy. But yeah, then you want to classify a point that goes slightly out of your interval, you have the same problem. So we don't just want to raise the line and realign it, so to speak. What we can do, we can apply a function over the output. We can apply a sigmoidal or a tangent-like function. it would look like this. Essentially what we do here, so now I use the logistic function, hence we're going logistic regression. Here I have my parameters, just as you know them from linear regression. I raise the output of linear regression to the power e. I divide this by 1 plus same thing. By definition, I have a probability. Everything is with a 0 and 1, sums to 1. Everything is fine and dandy. Looks like this. And actually, I even like the shape of this line better than the previous one, because here on the left-hand side, it basically gives a very low probability of defaulting, which is correct, right? That seems correct, intuitive. And the higher the draw on your credit card is, the higher, yes, that sounds good. That sounds good to me. So this trick, right? It's not like the stupid stats. I mean, and doctors don't want you to know about this trick. This trick is one of the most formidable tricks in machine learning and particularly classification. And well, we will revisit this a bit later. I mean, I have a nice illustration. I can let you hear what it sounds like, but we're not going to do this today. We're not going to do this today. So we have the probability, and well, not only the value is now sensible, we also get a few other ways to rewrite this thing that will become super useful. So here we have like the stupid fraction. We can actually reinterpret this as this thing over here, which is the probability over 1 minus the probability, which is the odds, or the odds ratio, right? Basically, if you go to the bookkeepers, right, you want to bet on a horse or something like this, right? Or on whether, I mean, a British prime minister will survive the shelf life of a lettuce, right? I mean, then you bet 1 against 10. That's basically what this thing does. All of a sudden, this looks already much nicer, right, than the stupid fraction, which I wouldn't know how to optimize. But we're still stuck with this e to the power. We want to get rid of it. We apply a logarithm. Done. And we have the log odds, or the logit. Logistic regression, right? You see where this comes from. So essentially, what we now want to do, we want to optimize this thing such that we get these probability values. That's what we want to optimize in the end, right? This is the variant of linear regression that we're looking at right now. And then we don't get linear regression as we knew it. If we get linear regression, nicely smoothed for classification. Okay, so let's interpret such a model. And afterwards, I'm going to tell you how we can fit one. We have our input variable x, right? We currently just have 1, right? We just keep it simple. We can make it multivariate in a bit. And we add 1 to it, right? So we had, let's say, x was 5. Now we go for x is 6. What happens? It's very easy to see. Namely, if x goes up by 1, we add beta 1 to the log odds. Okay. We multiply the odds by e to the power beta 1 times x. That's, or e to the power beta 1, because that's basically what happens. Okay, that is nice, right? I mean, for those of you who appreciate these things. What does this mean now on the actual probability? By doing this, we have a nonlinear effect, because we have this division and we have this raising to the power e. This means that if beta 1 is larger than 0, adding something to x will increase the probability. And if the coefficient is negative, it will decrease the probability, which actually is pretty good to know, right? This is kind of how you would like it. If you have a positive coefficient, there's a positive correlation, it derives probability. Oh, negative. Okay. This is good, this is nice. Okay, now we still need to find these coefficients, right? We now know how to interpret them, what to do with them. I kind of said, okay, we can now use the linear regression machinery to find them. That was a white lie. That was a white lie. In the end, what we have is the following. We can now, given a set of coefficients, I can compute for a given data point, what is the probability of this data point, right? But I think everybody will agree with me. I can't just do this for one data point. I can also do this for a whole batch of data points. I can do this for all my training data. And if I just simply take the product of all those probabilities, I have what we call the likelihood of my data set given the model, right? Now, this is an interesting type of interesting way to think about it, because that allows us to reason about what would be the right, or perhaps even the best coefficients. Very simple. We want, within our model class, those parameters that make the data as likely as possible. If we have coefficients that make the data less likely than strictly possible, yeah, why would we even want them? So this is exactly what we do in logistic regression. We make use of this probabilistic interpretation, and we're gonna tune the coefficients such that we achieve maximum likelihood. Effectively, what I just said is that what you have here, right, is the probability of x given the parameters. There we are. Now, one probability is between 0 and 1. If we take a product with another probability, then, well, it's also between 0 and 1. This very rapidly vanishes. We get extremely small numbers. It's not impossible to do computations with those, but you would need an incredibly high precision in your computer. Much more convenient to use the invention by Charles Napier, the logarithm. And all of a sudden, all these products that we have here become a sum of logarithms. This is called the log likelihood. And this is what we use in practice, right? Products over small numbers we don't like, just summing, fine. But, also the way that a logarithm works, right? The smaller, between 0 and 1, the closer it's to 0, the bigger the number that you get out of your logarithm. And summing big numbers, that is all fine, that is dandy. Now, in another way of interpreting this is not to just look at the log likelihood because it's convenient, but we can also look at the negative log likelihood. And what is interesting there, I see you frown, like, why would we do that, right? Yeah, because we can. Yes, but also because it all of a sudden allows a different type of interpretation. If we use a logarithm to base 2, rather than e or whatnot, right, to base 2, what do we get? Take the logarithm of base 2 of the probability. This is the optimal number of bits to send the message x, what is the value of variable x, right, using your current model. There's no way how to transmit this value more succinctly without loss. Claude Shannon, 1948, beautiful paper. I recommend you to look this up. A mathematical theory of communication. And even though many of you are still doing your bachelor's, this is a paper you can read. At bachelor level mathematics, you can read this, and you can understand this. And this is one of the most beautiful papers that I know, because this guy, he was brilliant, absolutely brilliant. I mean, everybody knows Turing, right? Oh, I would have liked to see those two in one room. But, and then John von Neumann too, and then observe, that would have been brilliant. Would have been brilliant. No, so Claude Shannon is the founding father, quite literally, of information theory. How can we measure complexity of objects in bits? How can we measure randomness? Beautiful, beautiful theory. And this paper, if you read it, Mathematical Theory of Communication, you can sort of get the feeling that this is somebody who wrote this was very smart, and they knew that they found something that is amazing, but they have a new toy and they can explain it quite well, but they don't really understand it yet, right? I mean, much more than you and I would had we found the toy, but it's beautiful. I strongly recommend that. It's completely out of the curriculum for this course, but still. So that's why we like the negative log likelihood. That's the number of bits. And hence what we now have, we want to find that set of parameters that minimizes the number of bits, that maximizes the compression. And I don't know about you, but personally for me, this is a brilliant interpretation. It makes it much easier than, yeah, I'm just going to maximize my likelihood. Because why? Compression makes sense in my head. But then again, I've been working on compression and information theory for more than a decade, so professional deformation of the mind. Good. How can we now optimize these parameters? Let's forget about the negative, right? We can just plug it in, there's no problem. What we typically do is we take a Newton-Raphson type of method, because the landscape is not necessarily linear. It is generally, depending on the problem, convex or convex-ish. Convex-ish is mathematicians hate this term, right? Because it doesn't exist, but it's convex enough for me to get a good model when I optimize in this gradient descent kind of way. Stochastic gradient descent makes use of this. Okay. Those of you who are, okay, what the hell is he talking about? Let's just imagine. Now, we want to maximize the likelihood, right? Log likelihood. That's what we want to maximize. This is going to look, in a very simple case, a bit like a cone. Just imagine a quadratic thing. Now, suppose we're currently, we have one parameter, right? I mean, I simplified matters completely. We are here, right? Where do we want to move? We want to move up, right? That's actually, I'm going now far ahead of my slides, but I'm already giving you intuition. I think this is a better moment to already explain the intuition. We want to go up. Well, that is going to be the sign of the first derivative. We need to go in the opposite direction. That's basically where we want to go. How much do we want to go up? Well, very much, of course, but we shouldn't get too eager. We shouldn't get too eager, right? So suppose that we're now, and the tip is really somewhere high up, right? When I'm here, there's a lot of action. There's a lot of action. I need to be careful, right? I shouldn't make too large a step because before you know it, I'm on the other end and then I'm just hopping back and forth. Okay, so the steepness of the curve where we are, that should determine how large the step is. Second derivative. First derivative tells us which direction to move, our coefficient. Second derivative, how quickly, how large are the step sizes. I have slides that explain this in a second, and I will re-explain it then, but now we already have the intuition. That's essentially what we're going to be doing. Now, how are we going to be doing this? We're going to be doing this over multiple parameters, so it's a little bit more complicated to imagine than what I just sketched. But essentially what we do, we're just going to step by step, iteratively, well, gradient ascent in this particular case, because we're maximizing the likelihood, gradient descent in the an error or negative log likelihood type setup, but step by step until at one moment we have converged. Now, if the problem is convex, like the one I asked you to imagine, then as long as we're taking steps where our score gets better, and we never take a step where the score gets worse, we're bound to find the best, right? But now you can also see that if the shape of this cone is not really a cone, it's a bit wiggly, right? It might be that at one moment, like, okay, well, this, so let's say it looks like this, right? So there is sort of a dip, and I get stuck here, right? And I'll never find the true optimum. I found a local minimum or a local optimum. Now, I said, okay, I like convex problems, because suppose that we now don't optimize completely correctly. I don't always take the step in the right direction. I don't always listen to either the first or second derivative, right? How large the step is or the direction. Sometimes I do something random, or in fact, I always add a little bit of randomness. Stochastic gradient descent. And you can already intuitively feel that, hey, if I'm stuck somewhere, right, rather than staying there, that I do something random, then I might be able to escape the local minimum and find, well, greener pastures, better points in my space, right? That's, in a nutshell, what stochastic gradient descent does. However, we typically don't add the noise in the optimization procedure. Typically, we let the data do it for us, but you can interpret it as now and then doing something stupid. Doing something stupid, right? I mean, there's the current meme, fucking around, finding out, right? So that, I think many of you will know it. It's a little bit like that, right? That's yeah. Good. And if you don't know the meme, then okay, you just bleep it out what I just said. Good. Yes, good. Now what do we do? So if we now steppity, at each of these steps where we changed the parameters, but we still have in the end under the hood a linear model. We still have the beta 1, beta 0, right? Just like we saw it, right? So we can use all the tools that we learned in the last few weeks to determine if coefficients are significant, yes or no. We can use this. We can interpret and we can use. This is nice. This is very nice, because we're not all of a sudden in la-la land where we have no idea what we're doing. The machinery is the same. Let me give you an example. So based on credit card or drawing balance, I mean, is somebody going to default? After fitting, what do we see? The estimated probability, given that somebody has, they already borrowed 1,000, versus somebody who borrowed 2,000, you see that the probability for the first one, very low, that they're going to default, because they're somewhere over here. And for 2,000, well, they're somewhere over here. It's not 100% like, oh my God, this person is never going to pay back, but right, we're taking a risk. We're taking a big risk. also within this model. So this is now the coefficient that we have here, right? This is beta 1. If we add €1 to their balance, essentially means that 0.005, so we have over here beta 1, gets added to the log odds, and so on and so forth. This is what I mean, that we can use all the machinery that we know, right? After optimization, especially, we can say, okay, what was now significant? Do we need certain predictors, yes or no? If we are comparing different models, we can do this, right? That's good stuff. Okay, good. I'm going to continue one or two more examples, then we're going to take a short break, okay? Now we're going to do the same prediction, but now not given credit card balance, but given a binary predictor, whether somebody is a student, yes or no. How can we do this? Well, if I would have asked the question, how can we do this for regression? You would have said dummy variable. So what do you say now? Dummy variable. Yes, correct, correct. We just plug that in. We just create our new x1 that is then 1 or 0 depending, and there we are. So what's now the probability of this? There we have this essentially 0.40409 times 1, because student is yes. Here it's times 0, so that entire term disappears. There you have it, right? So, it's a bit weird though, because we saw earlier that students were a bit special. Here we see that students have a much higher probability for, or much, I mean, comparatively, if you look at the odds, to default than non-students. As we'll see, this is actually wrong. Students can be trusted with money. To spend it on beer, perhaps, but I mean, anyway. Good. What do we have? If we now look at the analysis, this intuition gets confirmed. The Z statistic is very low, right? Or very low compared to previously. So 3 is still significant, but it's getting very close to the edge of significance as we saw it, right? You also see the p-value. It's small, so it is significant, but it's not super mega ultra significant. Good. Now, what does the multivariate version look like? Just like you would expect it. It's really there's no magic there. Absolutely no magic. So we just have more coefficients. We plug it in. It all looks the same. And now what we can see, if we look at the example where we look at predicting defaulting based on balance, income, and studentship, all of a sudden interesting things start to happen. Because what we now see, well, first of all, income is apparently not significant. Okay, that's in a way interesting. Studentship, well, still is, but it's also still, it's suspicious, right? I mean, that's one of the reasons why I like this example is if we would now be hardcore statisticians, we would have set our alpha as 0.00 something, right? Yeah, it's significant, we're done. But always plot your data and always interpret these numbers, right? Because just by looking at these numbers, okay, income is important. Studentship, if you're just ignoring the labels of these things, income and student. Are these things perhaps a little bit correlated? Do we remember the problem that we had in linear regression, collinearity? If you have two variables that know too much about each other, you can exchange the one for the other. Could it be that either neither of them are significant, or that, well, student is now giving the information in a sort of more easily digestible form to the model that actually you want to get out of income? Is there something fishy going on? This is going to be the final example. Why is it positive in the, oh yeah, this is another actually thing. That's here, the coefficient is even, now it's here negative and the other one was positive. There's another hint. That, but my trigger would really be the income student, there's something going on, right? There's confounding, obviously. I mean, students make less money, right? And actually, if you now look again at the data, students, here we have them again. The balance, the drawing balance is already quite high in general. The difference between the default and not so large. So there is something special there. Now, if you look And so basically what happens is that students default when they have a much higher balance, drawing balance, than, well, normal people, because they already loan quite a lot because they don't have so much income. If you don't take this into account, that there is essentially two populations in your data, essentially what's happening under the hood, your data is not fully IID. It's not identically independently distributed. There's not one homogeneous population. And if that doesn't hold, and again, all machine learning theory is based on this, just comes crashing down. You get nonsense output. Nonsense output that may look very good, like look how low the error is on our training data, but be very careful when you deploy this. If you now look at a specific fixed value of balance and income, it actually turns out that the student is less likely to default, which of course can be causally explained that, hey, student income is very likely to increase, whereas somebody, suppose they're already in their 40s or their 50s, and yeah, income may change, but not as dramatically as for a student. So in a way, it is much smarter to lend money to a student, especially those that have good career prospects. Just to show, in a nutshell, that we can use linear regression with a weird activation function, it's roughly how you can think about it, to do classification. And well, it once again shows the power of linear regression, right? We can use one variable, be it continuous, be it discrete. We can use the whole shabam. We can detect by interpreting the coefficients and using the statistical machinery you have, which predictors do you want to use, which should you be careful of, and so on and so forth. Later in this lecture, we're going to be checking, or perhaps even next week, I think next week I have a full-blown comparison of how good logistic regression now is in practice. Good. For now, let's take a short break. Let's take a 10-minute break, and then we reconvene and we continue. Yes? Okay. I would like to get started again, if that's okay with you. So there's technically 1 minute left. Just out of curiosity, because the world changed quite a bit in the last 2.5 years. I mean, you're well aware, not just for all of us, but definitely for us lecturers, because until 2.5 years ago, I didn't have a Zoom. I didn't have a Zoom account. I didn't have a YouTube account, and the whole idea of recording lectures was completely alien to me. And at first, we were all scared, not to say shitless about this, because by now, I've gotten quite used to it. And well, to say at the very least, I don't mind anymore. I'm just wondering, because you take the effort to come to the lecture, and hence this is a very biased sample. Do you actually use these recordings? Yes? Can I just get a raise of hands? Because I see heads shaking, but okay, this is okay. But there's also a number who don't. Okay, that's great, cool. Nice. Do you use it relatively soon after the lecture or more closer to the exam? No, of course, yeah, you're absolutely right. Yeah, I hate these types of questions. I always just answer yes when people ask a double question, so yes, I should not do the same. Do you primarily use this after the lecture, let's say the week or the 2 weeks after? Yeah, or primarily before the exam? Okay, okay, interesting mix. Okay, very good. One other thing, now that we're sort of in survey mode, actually this should be, that's good, okay. Now that we're in survey mode, so me, other colleagues, we've had long discussions on what is now the best platform to provide the video recordings. I went for easy. I like YouTube for this. Primarily because Zoom connects to YouTube very simply, and yeah, YouTube is pretty good for videos in my experience, right? There's others who prefer to put it either via Teams or some other server. I mean, so just to keep it a binary question, whom of you is, let's say, well, primarily happy with YouTube? Oh, okay, okay. Those of you who, okay, who isn't? Do we have? Okay, I'm not going to bite. I just wanted to ask. Okay, what don't you like? But okay, good. Done. Very good. Okay, no, thank you. I will also communicate this to my colleagues. Because believe it or not, I mean, we typically just fly blind, and many people either don't dare or forget to ask these things, and we just do what we think is a good idea. Good. So let's dive a little bit deeper into how do we fit a logistic regression model through maximum likelihood. The details of this particular part are best consumed through the ESL book. The ISLR book gives a decent intuition, and well, you get the main ideas, but to get it properly done, this is one of those things where you need to look into the ESL book. The intuition is exactly like I said earlier, right? We simply want to climb a very smooth mountain, or well, descend a very smooth valley, depending on whether to do negative or positive log likelihood. Well, what do we have? Let's unpack what we have. We have a log likelihood function, so curly L, it's typically curly L, which we define here over theta. Theta is the set of parameters we have, right? So normally we've been calling these betas, right? But now it's theta because it's in general, right? In linear regression, logistic regression, we have betas. Sometimes you also have gammas and whatnot, and the whole shabam of parameters we typically call theta. So this is the general formulation. And what we now essentially do, over each data point, we sum the logarithm of the probability of x given the parameterized model, or model parameterized according to theta. Then P is a density function, which basically just gives the probability, normally of class K, given some data points. You can also do it differently, but this is the general formulation. So if we now have a binary problem, well, how does this look? Well, so do we have a target variable y, which is either 1 or 0, right? Which means that, well, probability for a particular class is essentially that probability for the one class and 1 minus the probability for the other, right? So binary classification simplifies matters in this sense. So we're going to be using this to explain the basic ideas. It generalizes quite straightforwardly. You just have a few more terms to deal with. If we, in binary classification, plug this in, we're going to get this. We have a sum over all the data points. And what we have here is, let me see, where are we? We have the probability, this is the positive class, right? So basically when y becomes 1. And here, this is the negative class. Okay, why do we have these two terms here? Depending on whether we do this correctly, yes or no, right? How good is this probability guesstimate that we have? We can simplify this a little bit into, what are we doing here? Here I have my probability density function in general. I'm going to be plugging in logistic regression, right? So I don't have theta anymore in general. I know that I just have a few betas, right? I could replace theta with beta, but I mean, that doesn't save us much. Given that the way that logistic regression works, I just have a parameter vector beta, and that's what I'm going to be using. That's what I have here. So essentially the prediction is going to be yi times beta transposed times xi, and then the negative. So we have the positives and the negatives, they contribute separately. This is the parameter vector. We've seen this before, but I just wanted to make sure that you can also read the ESL book properly, right? I mean, thetas, betas, and everything. Xi, here I've made it bold. Here it's also bold, that's correct. If it's bold, it's a vector, right? It's the entire thing. What we very often do to make the whole analysis a bit more nice, we add a secret predictor that is always 1. I call that one capital X0. Not to be confused with small x0, like in nearest neighbor, right, which is the query point. Capital X0 is sort of like the 0th predictor that is always 1. Why am I interested in that? To make sure that I can guesstimate a baseline probability regardless what happens. No matter how stupid the other predictors are, I have a baseline. Helps the analysis. If you wonder, okay, so how did I now make this step from? I have a side calculation. I'm not going to walk you through it right now. If you really, really insist, then we can do it, but that's why I grayed it out. It's also the currently uploaded slides, they're grayed out. I'm going to grade them out a little bit less. When I re-upload the slides, right, you can look at them, then you can see what are the steps that I take. I even explain what I do, so it should be relatively easy to follow. What are we now interested in? So we have this new formulation, right? I mean, that's linear algebra. And, this is also the moment where I actually should have included the XKCD meme, like, well, this guy is standing on a big pile of stuff. What are you doing? Yeah, machine learning. And that's like, what is it? It's a big pile of linear algebra. And what if it doesn't work? Well, we just add more data, and that's essentially what machine learning comes down to. Linear algebra, add data. If it doesn't work, add more data. That's exactly what we're trying to break through, right? I mean, that's by doing research. So we're trying to find that beta that achieves maximum likelihood. How do we do this? Well, we can take steppity, but if we have a nice formulation, we can just find that point where the derivative is 0. That is the best point, right? Okay, why don't we do this? Well, this is what we have here. So the first derivative of the log likelihood over beta, and well, if you work it out, looks like that. Now, this thing you can break down, because here we again have the entire probability and now over beta. We can break it down into p plus 1 equations. P, because we're going to get 1 for each individual beta, right? And the 1, well, that's going to be the intercept, for which we secretly need this x0 to make everything work nicely. We know, this is basically where this x0, this big x0 trick comes in, right? We know that the first value is always going to be 1. So we also know, if we break it down, that this first equation in this batch is going to look exactly like this. It's essentially, the sum over all is 1. This is the sum over these probabilities. It's the expected number of class 1 assignments. Because that's what the probability of x does, right? Binary classification. First one is the probability for class 1. What is the probability for class 2? 1 minus. So here we just sum the probability. That's the expected number of class 1. If our whole data set, except for 1, is class 1, well, then this expected number should be very high, right? That's exactly what this x0 now allows us to do. We have one score equation, that's how we call these things, that can already set the, well, not so much the average, but the expected value. The other score equations are more interesting, of course. How can we set those in a good way, in a nice way? If the problem is entirely convex and it allows nice analysis, then we can find the derivative immediately, right? I mean, that's just analytically. It's often not the case. Maximum likelihood, almost never, I mean, unless the problems are completely trivial. So what we do instead is this hopsidy thing in multiple dimensions over multiple betas, right? So it's very difficult to imagine how this now looks, right? But the idea is that we're just climbing this very smooth mountain. Now, essentially what we want to have is that the new betas, or the old ones, look what we have here. We have the second derivative, that is the how much is it curving? So how careful should we be in our steps, right? If it's like we just discussed. And which direction? Yeah, the opposite direction as the first derivative. That's essentially what we have here. And we repeat this steppity until convergence, until, well, the likelihood ceases to grow, because then we've overshot. There's different ways, there's different variants of this general scheme, right? But, Newton-based optimization, I mean, gradient descent. I mean, there's a whole zoo of different methods. The general idea is all the same. In small steps, move towards a better place until you can't find a better place than where you currently are. There's different ways on estimating how large the step should be, right? Here it's the derivative, and as you will see, maybe even on this slide, I mean, this has to do with the Hessian. Oh, there it is, the Hessian. Why is the Hessian important? Hessian, as we saw in linear regression, that showed what is the contribution of certain parameters, of betas, to the output. I mean, on the variance, right? I mean, how much do we rely on a specific value? But, essentially, you can interpret this on how smooth are we? Where in the landscape are we? Are we relying too much on this, too much on that, or are we like, we're good? That's what the Hessian here has to say. But in general, forget about Hessian, or I don't know, maybe, I still actually don't know why it's called the Hessian. Was this somebody who came from Hessen? Something, I honestly don't know, I forgot, or I never knew. There are different ways of guesstimating, like how stable are we, what is the slope, right? Each of those ideas essentially define a new optimization mechanism. And for a very long time, and I'm talking like 30, 40, 50 years, the name of the game in machine learning was convex optimization or non-convex optimization, depending on which way you swung. How can we optimize better? How can we guesstimate the direction and the step size even better, such that we need fewer and fewer steps and we're less likely to overshoot, and so on and so forth. For a very long time, this was the name of the game. This, especially now with deep learning, has all but disappeared, because people have now accepted that problems are incredibly non-convex, and all this theory is beautiful on paper, but in practice, if we just throw data at it, let the linear algebra do its work, it's going to be fine. So it's a little bit the tension that we currently have. We have beautiful theory on how to optimize on very specific types of models with limited data, but in practice, if you have enough data, it doesn't really matter, almost. So we now live in the land where it does matter. And then after this lecture, this course is over, you can explore the rest of the world where it doesn't matter anymore. But at least you know that at one moment it mattered. And you will see that just throwing data at the problem, that's not the solution. That's for many, many cases. Good. Yeah. Log likelihood is concave. This means that we have a nice smooth. So basically, wherever we start with our parameters, we just keep on optimizing, everything is going to be fine, right? Convex, concave, right? Typically, we speak about convex problems, like convex better than concave. I don't know why, but maybe because there's an X included. No way. You can start with whatever value of beta you like. Beta 0 is fine. Of course, the better you can guesstimate the correct beta, the fewer steps you need. That's profit, right? And this is, again, a large and very fruitful subfield of machine learning, how to guess where you should start. Now, if your problem is not properly concave or not properly convex, if it's convex-ish, right, or non-convex, right, it has lots of these local minima, then, of course, guesstimating where you should start. And the optimization strategies, like where should you now tweak, right, how large a jump should you make, become more and more important. Overshooting can occur because sometimes you get in the situation where you just hop back and forth. You don't quite reach the best solution. You might say, okay, well, I don't really care. Yes, depends a little bit where. This hopsing occurs, of course, right? Do you know this before? No, you don't. So the general strategy is hence typically sort of like a simulated annealing type of approach of learning, or class of learning problems, where essentially initially we allow large steps and we dial down the temperature of the system, right? It's an idea from physics. We cool the system down so the molecules can move less and less. So basically we start to make smaller and smaller steps until the system is frozen. It's one of the techniques how you can break this jumping around. Good. Again, we can work this out. Linear algebra, but study this. For now, I'm not going to walk you through it. Unless you really insist that I walk you step by step through equations. I personally don't really believe that a lecture, a monologue from this side is the best way to do so. This is the type of stuff where a tutorial is better suited. And yes, they are then a bit lecture stylish, but this is also very studyable at home. Good. Now I'm already at, surprisingly, the last slide I planned for today, but I have more. We can continue. But basically the slides online cease to exist from now onwards, but I have more. We have two classes of classification methods, or at least that we've seen so far. Maybe there exist more, maybe not, doesn't really matter right now. We either have discriminative classification and we have generative classification. Where discriminative classification is a bit of a misnomer because effectively classification is discrimination by definition, right? You call something red or blue. you're discriminating, right? I mean, it's the one or the other. We don't allow for any room between them. Well, that room for in between them, this is a little bit what we use in this slide. Because if I say, okay, this is 80% blue, then allow for some room that is 20% red, right? I'm not entirely certain. That's what the generative or the probabilistic approach to classification is about. Essentially, what we're trying to do for an input or an out, for an input X, we're trying to find the label, and discriminative, we're trying to commit to the one label, right? So this is then G hat F whatever, right, of the class. So we want to estimate the class, and the main idea of these methods is that it just gives a value. Bam, this is red, this is blue, and however it gets to it. How do we measure whether these methods are good or bad? Well, either they get it correct or they don't, right? It's pretty, well, binary, you could say, in that case. We have a loss function. So we want to minimize the number of wrong predictions that we want to minimize, so that's what we do. Now, the slightly more open-minded version of this is what we saw already through logistic regression. We have all of some probabilities. So what is the probability of a student or a non-student defaulting? The output, in the end, we want to give a lone yes or no, but it really helps to model the world in a sort of bit more in shades of gray, right? 50, 42, I don't know. So what we're trying to do here, we try to find a probability distribution per class. So essentially the idea that we're following is that every class has its own distribution that generates points, right? We have the defaulting people generating distribution, and we have the non-defaulting people generating distribution. Together, if the right properties hold, we can see this as one distribution that can generate both, right? It can be a compound distribution. That's essentially what we have here. And then what we have is that, well, this is going to be the probability that an input X is going to belong to a class G. 80% red, 20% blue, green, whatever. Now, that allows us to also be a little bit more relaxed in the way that we, well, scrutinize or actually penalize the method, because now we can look at the likelihoods. If something actually was now, so we say 80% blue, but it turned out to be red, yeah, it was wrong. So if we really threshold, okay, bad classifier, bad, but in a way you could say, like, well, hey, it was 20% right. Huh? And just from a didactic perspective, it's better, right? So you can interpret it a little bit like you now handed in your assignment sheet, and we could grade it in a 0-1 loss. Did you do everything perfect or not, right? And you get all the points or none. It's one didactic model, right? It's pretty hardcore. We don't do this, obviously, right? Because, yeah, that would be potentially a bloodbath or not, depending on whether how smart you are, how bad we were / good we were with the assignment sheets. You want to give, let's say, fractional points, ideally, right? This is what we do in this probabilistic setting as well. So on the right-hand side, it's typically a bit more smooth. That's good in many cases. However, that does require, in this entire column, these P's, these distributions, these density functions, where we need to estimate them from data. They don't come out of nowhere. We need to make assumptions. What shape do they have? Which parameters do they have? Otherwise, we don't get probabilities. They don't come for free. So in a way, on this slide, we want to be on the right-hand side, but the right-hand side requires us making assumptions that we may not be comfortable in making, and hence the middle column is not so bad after all. Now, there's also plenty of methods that I don't fit on this slide that are somewhat in the middle, right? It's not quite probabilistic, but you have a slightly more relaxed loss. And note, by the way, that what I just said, the joke that I made, okay, linear algebra with lots of data. When do you think the discriminative approach with a hardcore 0-1 loss function is going to work better? Small data or lots of data? Is there a difference? Yes? let me repeat. Let me try to rephrase, right? So basically intuition is more data, better. Because under the hood, now it's the paraphrasing and the interpreting, if we have so much data, I mean, one error doesn't matter so much anymore. And this kind of turns into estimating a probability, not for an individual point, but more over the data. We smooth the errors out in a way. Lots of data allows us to smooth things out. Is that roughly what you meant? Or is this like, yeah, great idea, but this is totally not what I had in mind? Okay, good. It goes into the same direction. Okay, good. Then, but yes, this is exactly what happens. So if you now have very little data, think again of bias and variance, right? Very little data. Yeah, we need stronger assumptions, right? We need to assume already what the data looks like. What is the distribution of it? And then we can use very few data points to guesstimate these parameters. You could say this one over here is a little bit more the non-parametric version. We make fewer assumptions and we just say like yes or no, but we don't really know. I mean, like if I say something, well, this is my jacket is red. Yeah, is this now 20% wrong, 30% wrong? No, it's 100% wrong, right? In a way, it's much easier to define like bam bam, and then just with plenty of examples let your method figure out what is right, what is blue, and what is red, rather than trying to fit the distribution of different sets of objects. Good. Actually, it's almost quarter to 6. Yeah, I'm just going to stop. This is perhaps going to be the first lecture ever for me that I'm going to stop before it is time. So this is a unique moment. So I'm very tempted to continue, but then it's definitely going to get 6. And yeah, let's not do this to ourselves, right? I mean, let's pick it up again next week. And then we continue and wrap up classification. One announcement before you get up, one announcement for the week after. So next week I'm going to be here. Everything is normal. The week after, I'm not going to be here. And originally, I planned, actually I can even say, right, I'm not going to be here because I'm going to be in the US. I'm going to be in New Orleans. So the one major, like the biggest and most important conference, research conference on machine learning, NeurIPS, for Neural Information Processing Systems. Don't ask why it's not just called machine learning, doesn't matter. That's that week. And we have a number of papers to present. And well, I need to go there, I want to go there, I want to meet people. And that means that, yeah, I choose them over you. Yes, my classifier said yes, I'm sorry. It's harsh, I know that. Originally, I thought that I would just lecture from there online over Zoom, but I don't think this is going to be to anybody's benefit if I do this on my hotel room with a potentially spotty Wi-Fi connection. So what I'm going to do instead, next week, I'm already going to record the lecture for the week after. And well, I'm going to put it online whenever I'm happy with the editing, right? So that's going to be a pre-recorded lecture, which kind of sucks, but yeah. Okay, why? You perhaps at the beginning of the lecture, you saw that Alexander Borchevsky was here, right? When you remember him from the video, yeah, he's also going to NeurIPS. So we had one other backup option to ask yet another lecturer for one guest lecture, but we decided that, yeah, then you see too many different faces, too many different style changes. So let's not do that. So in the end, is it optimal? No, but I think out of all the options, this is the best choice for everybody. Good, so did you know, right? So don't miss me too much, but good. See you next week. Bye.